Welcome to Spring LIB.
Okay, in this problem we have a square of charges with side B. We were asked to find first the total electrostatic energy of this configuration. From there, we are asked if we were to put a charge at the origin, what would the total electrostatic energy be due to the five-point configuration. And then we're asked if we were to push that point at the center of the square, offset it a bit, would this be a stable equilibrium or would it be unstable? So to start, we can begin constructing the total energy. Recall that the electrostatic energy between point charge is Q times V, which would, for the potential of a point charge, a pairwise electrostatic energy would be simply Q1, Q2 over 4 pi epsilon naught R between them. So we're going to have to do this for every single pair combination of our on our square. So our total electrostatic energy will be 1 over 4 pi epsilon naught Q1, Q2 over R12 plus Q1, Q3 R13 plus Q1, Q4 R14. Now we have to consider some cross terms, Q2, Q3, R23, Q2, Q4, R24, and lastly, Q3, Q4, R34. Okay, so fortunately, for the first couple of terms, the same distances, and also these are all the same charge, so that makes things useful. We can pull a Q squared out, and we got 1 over B plus 1 over root 2B plus 1 over B plus 1 over B plus 1 over root 2B plus 1 over B, where the 1 over B distances are between sides, and then we have cross terms of the 1 over root 2B. Just a bit of geometry, and this all simplifies down to Q squared over 4 pi epsilon naught 4 plus root 2. Oh, and we can pull the B out. Cool. And that's the electrostatic energy due to the 4 charges in the square. Now, if we add a point to the origin, if we add a charge to the origin, its electrostatic energy, the U5th, would simply be 4, would be that we would have to consider contributions of the 4 other charges. So we'd have to take into account each of these distances, which are going to be root 2B each. So we would have Q squared over 4 pi epsilon naught B times 4 root 2. This is what we would have to add, the energy to add to place it there, because it's going to have interactions with 4 other charges. Okay. Now let's think about if we moved this charge in any direction, what would happen? Well, if we moved it so that it was slightly closer to one charge, it would be pushed back because all these charges have the same sign. It's a repulsive force. So if it was any closer to any charge, it should be pushed back with greater force, which would expectedly push it back to its original position right in the center. This is also the minimum energy state. When the particle is at the very middle, the total electrostatic energy is at a minimum. This is where the system is the most relaxed. So for these reasons, we call this a stable equilibrium, because if you try to destabilize it, it will stabilize itself. Stable equilibrium. And that's it.